Good afternoon, PyCon. Please welcome Steven Sklar here to share with us the Hare wins the race, getting the most out of RabbitMQ in distributed applications.
Thank you. Hi, my name is Steven Sklar, and I'm here today to talk to you about RabbitMQ and how to use it in your distributed applications written in Python. But before I get started, I've always wanted to say this from one of my favorite movies, Spinal Tap. Hello, Cleveland! Hopefully, hopefully this talk goes better than Spinal Tap trying to find the stage. Now that we've gotten that out of the way, a little bit about me. I am a development engineer at Predata, a New York-based startup that specializes in alternative data and machine learning. We make extensive use of RabbitMQ to orchestrate asynchronous work done throughout the day and also during our nightly machine learning pipeline. Here's a brief overview of what I'll be covering today. First, I will provide a general overview of RabbitMQ concepts for those who are unfamiliar with it or need a quick refresher. Then, I will demonstrate how to interact with RabbitMQ through Python. I will then talk about the Python library Celery and how it uses RabbitMQ to run remote tasks on remote servers. I will then use a short case study to demonstrate some more advanced use cases of RabbitMQ. And finally, I will review a few gotchas that I've personally encountered while working with RabbitMQ. How many of you have ever worked with RabbitMQ before? Oh, wow, great. Very cool. For those of you who haven't heard of it and are asking, what is RabbitMQ? The answer is, RabbitMQ is a message broker. What's that, you may ask? Basically, it's a server that receives, routes, and delivers messages to and from various components of a distributed application. There are currently a few message brokers out there today, including RabbitMQ, Apache Kafka, Amazon SQS, Google PubSub, and ZeroMQ. There are benefits and drawbacks to each of these, which honestly could be the topic of an entirely separate talk. So today, I will solely focus on RabbitMQ and its uses in the Python ecosystem. RabbitMQ was written in Erlang in 2007 and is released under the Mozilla Public License. According to their website, it has at least 35,000 production deployments, making it, quote, the most popular open source message broker. So now I'll review some of the basic building blocks of RabbitMQ. And I'll start with producers and consumers. This part is easy. Producers are simply applications that send messages to a RabbitMQ broker, and consumers are applications that receive messages from one. These are your applications really written in any programming language that need to send and receive messages to and from each other. The next RabbitMQ object is namely a queue. Queues are objects that live on the RabbitMQ broker and store messages for consumers to retrieve. Like a standard queue object in computer science, they are FIFO, first in, first out. Queues have specific properties that can be set at creation time. The most basic is the queue name, but you can also set a queue to be durable, meaning that it will persist if the broker restarts or crashes. Exclusive, which means that the queue can only be used by one and only one connection. And auto-deleting, which means that once a queue has been used, it is destroyed once the last consumer disconnects from it. RabbitMQ also supports optional arguments that are used by various plugins throughout the ecosystem, some of which I'll go over later in this talk. The next building block that I'd like to discuss is an exchange. Exchanges are objects that accept messages from producers and then route those messages to the appropriate queues. In RabbitMQ, it is important to note that producers do not directly send messages to queues. Instead, exchanges are responsible for routing messages to the appropriate queues, and producers then send those messages to exchanges. Like queues, exchanges can also have properties like durability, exclusivity, and auto-deletability. There are multiple types of exchanges, and each type routes messages in a different way. But before I get into those details, I want to quickly introduce you to one more important concept, which is bindings. A binding connects an exchange to a queue and contains additional metadata, such as a binding key. A queue can only receive messages from an exchange that it is bound to, and an exchange can only send messages to the queues that are bound to it. The binding key is used by the exchange to deliver messages to the appropriate queues based on the exchange's type. So now that we've covered bindings, we are ready to review the different types of exchanges. 3 of them that ship with RabbitMQ are direct, topic, and fanout, and each one of these processes message routing keys differently. First, we'll talk about direct exchanges. A direct exchange reads the routing key on a message, finds the binding or bindings with the same binding key, and routes the message to the queue at the other end. So in this case, a message with the routing key foo.bar will be routed along the foo.bar binding to queue A. Similarly, a message with the routing key foo.baz will be routed along the foo.baz binding to queue B. Now we're going to change the routing for QC to foo.baz as well. This is to show that multiple queues can be bound to an exchange with the same binding key, so both queues B and C receive that final message. Next, I'll talk about topic exchanges. Topic exchanges work similarly to direct exchanges with one important difference. The binding key accepts 2 wildcards. An asterisk can take the place of exactly 1 word, and a hashtag can substitute for 0 or more words. Words are separated by periods and limited to 255 bytes in size. So in the previous example, foo, bar, and baz are all examples of words. A topic exchange behaves exactly the same as a direct exchange if no wildcards are used in a binding key, so all of the previous bindings, foo.bar and bar.baz, are all completely valid for both direct and topic exchanges. However, the 2 wildcards in topic exchanges can be used in extremely powerful ways. So let's walk through these bindings from top to bottom. The first one, all messages with routing keys starting with the word foo will now be routed to queue A, regardless of their length. And this also includes routing keys with only 1 word, foo, since a hashtag can match 0 words. All messages with routing keys that end in baz will be routed to queue B. Again, this also includes messages with a 1-word baz routing key. QC is a little different. Since an asterisk can only substitute for exactly 1 word, this binding matches only 3-word routing keys that start with foo, have another word in the middle that's substituted by the asterisk, and end in baz. So let's look at some examples. Here, a message with foo.bar with a foo.bar routing key only matches the binding to QA since it starts with foo and ends in anything else. Routing key bar.baz only matches the binding to QB since it ends in baz and begins with anything else. Both of these messages did not get routed to QC because QC requires a routing key of exactly 3 words, and those only had 2. So, foo.baz now matches both queues A and B because it begins with foo, so it matches QA, and ends in baz, and it matches QB. Foo.bar.baz now matches all 3 bindings, so the message gets routed to all of our queues. Finally, I'd like to discuss fanout exchanges. A fanout exchange simply routes any message to all queues that it is bound to and just ignores the message's routing key altogether. So in this case, our message will be routed to queues A, B, and C. This can also be replicated with the topic exchange by setting all of the binding keys to hashtags. Because remember, a hashtag can match 0 or more words, which in effect matches every single possible binding key. So again, to wrap up, a producer sends a message to an exchange, which routes it to a queue that it is bound to. A consumer then reads the message off the queue. RabbitMQ also ships with a very handy management interface. It shows the status of all connections, exchanges, and queues in real time. In a default installation, it is reachable on port 15672 And personally, I found it extremely useful, and I highly recommend taking a look at it if you have RabbitMQ installed on your machine or server. So now that I've covered some of the RabbitMQ basics, let's explore how to harness its power in Python. The default way to communicate with the RabbitMQ broker is over AMQP, or Advanced Message Queuing Protocol. AMQP is an open source protocol that was developed in the early 2000s and first published in 2006. The 1.0 spec was released in 2011 and is the current version to date. There are several libraries in Python that implement AMQP. LibRabbitMQ provides Python bindings over the LibRabbitMQ C library, which is written in C. PyAMQP is a pure Python implementation of LibRabbitMQ. Pika is also a pure Python solution, but abstracts away some of the low-level connectivity functionality that you need to implement by hand in the previous two. Kombu provides an additional layer of abstraction over the AMQP protocol itself. It is used as a general-purpose messaging framework and supports additional protocols, including ones backed by Redis, Amazon SQS, Pyro, and others. So now I will review a code example that will demonstrate how to send and receive messages from a RabbitMQ broker using the Pika library. If you'd like to follow along with the actual source, all code is available on my GitHub in the RabbitMQ presentation repo. Also there is my lovable dog Nacho, who I'm kind of obsessed with. First, we need to set up the environment. In the init RabbitMQ function, I use Pika to open a blocking connection to RabbitMQ and use that connection to open up a synchronous communication channel where all activity takes place. I use that channel to declare a queue and a direct exchange. I then bind those two together with a simple routing.key, so that any message sent to my exchange with a matching routing key will get routed to my queue. Next, I built a simple producer class. This producer accepts a blocking connection object in its constructor and has a method to send a message. In order to send a message with this method, we need its content, the exchange name, and the message's routing key. Given that information, we publish the message to the specified exchange and then close the channel. Next, I build a consumer class. Like the producer, this accepts a connection to the broker in its constructor and has one method, getMessage. GetMessage accepts one argument, which is a string containing the name of the queue that it will attempt to retrieve a message from. Inside this method, we create another channel and execute a basic get. If there is no message on the queue, frame and body will be none and the function will return none. But what makes RabbitMQ so reliable and powerful is its message acknowledgement feature, which you can see in the second to last line. Here, once we've successfully retrieved a message, we send an acknowledgement back to the broker that says it's okay to pop this message off the queue. If our connection is interrupted between the time we get the message, but before we acknowledge it, RabbitMQ places that message back on the queue for another consumer to read in the future. This way, we can guarantee that any processing related to that message has been completed in full as long as we acknowledge the message after processing is complete. This is a very useful property when using Amazon Spot instances, for example, which have undefined lifespans and can shut down with only short notice. So to run this example, we first have to set up our RabbitMQ environment using the init function we wrote earlier. We then create a connection, instantiate a producer, and send a hello world message, of course. Finally, we instantiate a consumer, attempt to retrieve the message off of our queue, and print the message. So if you run the code in GitHub, you'll get hello world. So now moving on, one of the main places that you'll see RabbitMQ in the Python ecosystem is in Celery. How many of you have ever used Celery before? Wow, okay, that's a lot of people. For those of you who haven't, what is celery? Yes, it is a vegetable that is very tasty with some peanut butter, and I can hold the raisins, I don't really need them. but Celery is also a library that allows you to run functions on remote servers. It also lets you link together tasks to create larger workflows. There are Celery plugins for a variety of the most popular web frameworks, including Django, and it works well with Flask. And you actually don't even need a web framework. You can just import the library and start using it. The basic building block in Celery is a task. To declare a task, all you need to do is wrap a function with Celery's task decorator. Now you are ready to run this function locally or remotely and add it to workflows that link together other similarly wrapped functions. So here, by calling delay on the create user task, we are instructing Celery to run this task remotely. This means that Celery will send a message to an exchange with instructions on which task to run and any args and kwargs passed to the function. As we saw earlier, this message will also contain a routing key, which routes the message to the appropriate queue based on the exchange's type and its bindings. A Celery worker watching a queue will then retrieve the message, deserialize it, run the function, and store the result in a storage layer such as Redis for the client to pick up when it is ready. Celery is designed to work with its out-of-the-box configuration and ships with some sensible routing-related defaults. When using RabbitMQ as the message broker for Celery, by default, Celery creates a single exchange and a queue for all tasks, conveniently named Celery. While this is fine for most workflows, as we shall soon see, this can cause problems in larger or more complex systems. Now that I've introduced some basics, I'd like to use a case study to demonstrate how to use RabbitMQ to its full potential. While this case study uses Celery as the mechanism for interacting with RabbitMQ, the concepts presented here are applicable to any application using RabbitMQ through any of the libraries that I previously mentioned. If you're following along in GitHub, I don't see too many laptops out there, but hopefully somebody is. This example is under the Celery example initial directory. In Celery's default configuration, all tasks are sent to one queue. As you can imagine, this can cause several problems. The biggest one we encountered was that all of our workers would get backed up running long tasks like fitting a model, and other tasks would get stuck on our RabbitMQ queues until a worker freed up. This would lead to degraded website performance, since many of these background tasks actually return results that are used on our client-facing front end. So let's see how this setup looks like in code. Here's our basic Celery configuration. It contains our RabbitMQ broker's URL, a list of Python imports for workers to use, and a backend for storing asynchronous results, which in this case is a simple SQLite database, but could be something larger like Redis in production deployments. Here, I define two mock tasks that are proxies for other jobs in the system. In this example, the fit neural net task is meant to take significantly longer than the run user query task. To run this example, we launch a series of Celery tasks, each one sending a message to our exchange. I have a worker with 4 threads listening to Celery's default queue, running tasks as they hit the queue. So let's see what happens. So here you can see our Celery worker has started, and it's just sitting there fitting neural nets with all these queries now just kind of stuck on our queues. Our website is slow, our clients are unhappy, and my boss is unhappy, but now here we go, our queries have ran. So again, for the more visually inclined, this is what's happening. How can we use RabbitMQ to solve this problem? One solution would be to use 2 queues, one for fitting our neural net and another for processing smaller, quicker tasks. We would also assign one of our workers to this second queue, so queries could be processed at the same time that other workers are fitting neural nets. So how can we set this up? For those of you following along, this code is in the Celery example optimized directory. Celery provides options for users to define their own custom routes. Using these, we can now route model fitting and other computationally intensive tasks to one queue and smaller, client-facing tasks to another. We can optimize this even further by using more powerful workers to fit our neural nets and smaller instances to perform basic database queries, which may even save us some money. A Celery router, like this one, is a function that accepts some arguments related to the task that you want to run, and it returns a dict with information like the message's routing key and exchange that you want to send the message to. Celery then uses this information to send a message to an exchange that contains data on which task to run, how to run it, and any related args and kwargs that will be passed to the function. All of the work seen here happens at the producer level in Python code in the Celery package. Once the message is sent to RabbitMQ, the calling function continues to run and the message moves through the RabbitMQ broker to a queue bound to the exchange that the message was sent to. Here, it will get picked up by one of our Celery workers, which will run the task and store its result in our storage layer. Now, going back to our function, in this case, all this function does is return a dict specifying that all messages should be sent to our new smart exchange, with a routing key equal to the task's fully qualified name. So now that we have our router written, we do need to add some code to our Celery config script to set up our new RabbitMQ exchanges and queues. Here, we declare a topic exchange called smart. Remember, this type of exchange has the ability to process keys with wildcards. We then tell Celery to use our new custom router instead of sending all messages to the default Celery exchange. And finally, we set up two queues, one for processing neural net tasks and the other for performing fast queries. Since we are using a topic exchange, we can use a hashtag at the end of the namespace so that all tasks in the neural net namespace get routed to the neural net queue, and likewise for all tasks in the web app namespace. This is just an example, but as you can see, you can really get as specific or general with routing keys and Celery configurations as you like, depending on what your environment needs. And also, one thing to note, even though we do instantiate a queue object here, the library kombu creates the binding between the queue and the exchange specified in the args, so we don't have to worry about explicitly declaring them. Here's what the new configuration code looks like all together. As you can see, we have our new smart topic exchange, our new Celery router now on the producer, and our two queues with the appropriate bindings to this new exchange that we made. Another difference in this example is that we need to run two separate worker processes instead of one. We assign one worker to read off the web app queue to guarantee that there is at least one worker available for running small tasks. The second worker is listening to both queues, which is the default behavior and the configuration that we used in the previous example. Since we can specify the number of threads for each worker, we can still use 4 threads like we did before, but now we're just allocating them to do different jobs. In practice, again, you can run different processes on different machines as well, allocating more powerful workers to run our fitting jobs and smaller workers to run simpler tasks. So now, let's see this in action. So now we have 2 Celery workers starting, and all of our queries are running, and we're fitting neural nets all at the same time, and everybody's happy, our data scientists and our clients. One obvious downside of this is that you only dedicate 3 threads to fitting neural nets instead of 4. So it does take you longer to run all of your fitting work than before. But as we all know, computer science is full of such trade-offs, and you need to figure out what's important to optimize on in your particular case. In these last few minutes, I will go over some of the gotchas that I have encountered while working with RabbitMQ. This isn't meant to be an all-encompassing list, but it's more to demonstrate a few problems that I have encountered in the past, personally. What if your message doesn't get routed to a queue at all? One of the biggest risks in this new configuration is that a message simply never reaches a queue. This is because RabbitMQ does not guarantee that a message sent to an exchange will have a matching binding. While RabbitMQ will log this as a warning on the broker, a badly routed or drop message can cascade into some fairly large and hard to debug problems. Trust me on this one. One solution that I found is to use an alternate exchange. This feature is actually a RabbitMQ plugin that ships with the standard installation of the broker. All an alternate exchange does is reroute any unrouted messages from one exchange to another. To implement this, all we need to do is add the alternate exchange property to a new exchange, with the value being the name of the fallback exchange. So now, any message that doesn't get routed by the new exchange will automatically get routed to the alternate exchange, which uses its own set of bindings to queues. The message will then get routed based on those bindings and the alternate exchange's type. Don't forget to actually declare your alternate exchange and also bind it to a queue that some worker is listening to. Otherwise, you just end up with the same problem, but now on your alternate exchange. I don't have time to walk through a full demo of this, but I do have an example of how to use it in practice on GitHub in the aeexample.py file. Another thing to watch out for is that RabbitMQ objects are immutable and cannot be changed once they've been declared. This can be a benefit when writing code that talks to RabbitMQ, because you can redeclare a queue or exchange as many times as you want, knowing that a duplicate won't be created. However, this can cause problems if you change a property in code while redeclaring an object. If any property of your new object does not match the property of the existing object on the broker, RabbitMQ will return an inequivalent arg error, and the software library you're using will probably raise an exception. To change properties on an existing object, you must first delete the object and then declare it with the properties that you want it to have. Another problem we had is managing complexity. With multiple exchanges, queues, and bindings, our system grew fairly complex very quickly. As task namespaces changed, with more refactoring, imports needed to be updated on the workers. As we added more queues and exchanges, we needed to update the commands that launched them, that launched our workers to reflect the new desired behaviors and routings. It's a really tricky problem, and honestly, I'd love to hear your thoughts if you want to discuss this after the talk. I'll be right out there somewhere. Some ideas that I've thought of are using metaprogramming to generate a Celery config file based on some persistent data that describes your infrastructure, or using more advanced routing functions that return routing keys other than a task's fully qualified name. So in conclusion, I hope that you now have an understanding of what RabbitMQ is, how it works, and how to interact with it while working in the Python ecosystem. I want to implore that RabbitMQ is much more than a message transport for Celery and can be used in a variety of creative ways, wherever some sort of inter-process or inter-application messaging is required. And I will end with some pictures of my dog. Thank you.
Steven's going to be available for questions outside or offline. Let's all give him another round of applause.